Okay, so we are going to cover the concept of univariate stat analysis. So as we said earlier, data science tags. Again, we have description, estimation, prediction, classification, clustering, and association. I'll wait for a few seconds if any question on this. I think we covered the concept of this already last week. Let's wait for a few seconds. We know that, for example, in the description task, normally we are trying to find ways to, I would say, ways to describe the patterns or if there's any trends within the data. So description of patterns and trends often may suggest, again, possible explanation for such patterns of the trend, as well as it may be possible recommendation for policy changes, etc. Estimation, we're going to discuss that today. After that, will be more into stat concept. We also talk about prediction, classification. I think both of them are again supervised learning, as we said last week or last 2 weeks. We talk about review of machine learning. Prediction, normally, a good example would be regression, where our target variable is again a numerical value. Classification, target variable will be categorical. Then we also, so far we haven't covered clustering much, but cluster will be unsupervised learning. And also the concept of association. Association can be used as a supervised or unsupervised learning. Depends what we are doing. So the stat approaches to estimation and prediction is what we focus here. So, for example, now one thing, as we said earlier, from the syllabus, we cannot cover everything in 1 week. Actually, 3 hours. So, just this slide, the reason I want to mention this, I want us to see, I think I did across the syllabus. Okay, forget. But again, hopefully everybody understand what I'm trying to say here. There's no way we can cover descriptive statistics, inferential, probability, no. So we just want to summarize everything. So we will not go detail, for example, estimation, point estimation. We know interval. Also, you find a confidence interval, alpha value. So we will not go through details. Yeah, we're just going to talk in kind of abstract level, a high level. So we know the methods here can include the point estimation, confidence interval estimation for population mean or proportion also. Also, how to reduce the margin of error of a confidence interval. And normally we have the alpha value also. If we say the confidence is 95% interval confidence, then we will say the level of significance then will be 5% or 0.05 most of the time. We're also going to examine hypothesis testing. Again, we can't go details. For example, when we talk about parametric testing, we normally start the hypothesis testing with a z-test, standard normal curve z-test. Then we go to the z-test. Normally, you need the population standard deviation, which is sometimes difficult. So we don't normally use the z-test. I'd rather use t-test, or we rather use t-test. We can use t-test for one sample. We can use t-test for per sample, or t-test for independent sample, two sample. So when we say two samples are independent, means they can come from different population, and the size also can be different. But per sample or dependent, it means they have to come from the same population, and the size of the two samples must be the same. When the sample is more than two, then maybe we may consider ANOVA, analysis of variance, the F-stat. What again? So again, we can't go detail on this, but we may discuss that along the way. Non-parametric tests now, we can talk about sign tests, Crucial, etc. So again, let's see what we have here. So we know, again, we won't go detail, but we are going to examine some hypothesis testing for both mean and proportion. So when it comes to hypothesis testing, we will say that's the start inference, because with hypothesis testing, our goal is that we are going to take a sample. And most of the time, we cannot do research with a population because population is too big. Collecting population to take a long time and it will consume more in terms of finance and time. So we are going to take a sample, and hopefully the sample will represent the population, which means there's no bias. Then we can use, again, that sample, test the sample, get some result. Then we apply that result again to the population, generalize it. So that's the main goal. And also in hypothesis testing, I think there's a basic 4 steps we have to follow. One is we need to state our claim. Normally our claim will be the null hypothesis. Then we have to have the alternative hypothesis, which always will go against the null hypothesis. And also we have 3 types. We have the two-way test, like if HO equal, the mu equal to 0, not equal to 0, so it will be two-way, or greater, less than, one way, etc. And normally the first step, we state the HO and HA. Second step, we can find the test statistics. For example, if we are doing t-test, we can find the t-statistics. Then also we can find the critical value. Based on the critical value and the t-test, t-stat, we can know whether we are going to fall under the rejection region or accepted region. Now, when I say rejection, means whether we're going to accept or reject HO. Normally, we always either reject or accept HO based on those 2 values, critical value and the tester. Sometimes also, if you are using the software, I think we can go ahead and find a p-value. Then we know the alpha. The alpha will be the level of significance. Most of the time, it will be 0.05. So if we know that, if the p-value is very small or less than 0.05, then we have to do what? Reject HO, which means the test is statistically significant. If the p-value is big and than the 0.05 or the level of significance, then we fail to reject HO. Yeah. So that's again, all these things goes detailed as a formulas, but again, we are not going to go details on this. So here, what we say is that the start inference consists of one method for the estimating or testing the hypothesis about the population characteristics based on what the information we get from the sample. So that's the goal of hypothesis, or even inferential statistics. Always we use sample, test the sample, the result we get, we apply it to the population. Here they say, what is a population? So population will be everything. It can be people, persons, item, or data. What is a parameter? That will be the characteristics of a population. So for example, the mean of the population can be parameter. The same thing, we have sample. So sample will be the subset of the population, which will be part of the population. Also, the term statistics is the characteristics of the sample. So statistic is a characteristic of a sample. So we talk about the concept of point estimate. So point estimation always refer to what? That's why it's called point estimation. Always refer to a use of single known value of the statistics to estimate the associated population parameter. Then we have the interval one. So this is just, I would say the unit. Mean for the sample is X. For population mu, standard deviation is lowercase s. For population, standard deviation will be sigma. Proportion P. For proportion for sample is P, lowercase p. Then for population will be power. So this is the symbol we're going to use in this slides for, in case we have to, again, find it. So here we say any sample characteristics is a static, which under the appropriate circumstances can be used to estimate its respective parameter, which is the population. Now, one thing is that population is always fixed. The mean, the value here, population mean, standard proportion is always fixed. Sample will change. For example, if you collect 2 or 3, let's say 2 or more samples from the same population, let's say the sample size is 10. Most likely, the mean of all the 10, of all the 3 samples you collected will change. It will not be the same. Our goal is that they should be close to each other, so we can approximate it. Yeah, so point estimate will nearly always miss the target parameter by a certain amount. Also, we have the concept of sampling error for the mean. That will be the distance between the observed sample mean and also what unknown population mean. Always the value is positive. Also, point estimate have no measure of confidence in their accuracy. We can't say 95% confidence, no. So point estimate is that tips and aiding the bullseye or the target parameter. Yeah, this is better, confidence interval. So BMOG, more area than that tips, so more confidence than the boost is it. Wait for a few seconds. If any, again, as we said earlier, this slide is not meant for statistics top subject. We just glance through. We have to do statistics only 1 week. So, okay. So we get the idea of confidence interval. Straight, this will be the idea. For example, point estimate, then plus or minus some margin of error. So we can set it 95% confidence interval there. So confidence interval estimation can be applied to any desired target parameter. And also its most widespread interval estimate. The keyword, it consists of interval of numbers. So we can say the mean value is between 20.3 to 32, or 20.3 to 22.6. So there's some interval there. Instead of saying the mean is 20.3, point estimate. So it's easy to miss the target with point estimate, the actual one. Okay, so they gave us the formula yourself there. So this is, if we're doing T, so the margin of error E for 95% confidence interval for the population of mean will be this. Normal, I think it will give us 1.96. If it's 0.05 over 2 with a T, we know the X. So this will be our standard error value. So we say for N is what they call it, the sample size, square root of the sample size. Yeah. Now they gave us 2 ways to decrease the margin of error. I think that's our goal here. By decreasing the confidence level, which of course will reduce the value of and also therefore reduce the E, but this is not recommended. Recommendation, increase the sample size. As we said, if we use the whole population, I mean, we will not worry about error. The population always, but since it's not feasible to use population, especially if we have a large population. But we know from statistics, by increasing a sample, that will help us reduce the errors or fluctuation up and down values, not staying constant. So here they say increasing the sample size is the only way to decrease the margin of error while maintaining a constant level of confidence. Again, here we have the population proportion formula. So here we are using Z instead of T. So population, let's say population proportion plus or minus Z alpha over 2, P times 1 minus P over N, which is the sample size. Yeah, as we said earlier, always 95% confidence interval. If alpha is 0.05, the Z always you get 1.96. That's for Z, not for T. Sorry, I think I was mentioning T. Yeah. Again, we don't have the value, so we can't, we don't have the data set to go through this, so that's why I'm skipping the example. But it's the same thing, the formula here we are using. If we know the value for P, then 1 minus P, then over N. So that's, you can see, if you had 0.85551 to 0.144, now you get 1. The sample size is 3,333. So you can see at the end, we got some interval value here between 0.1329 to 0.1569. So that's the whole concept of confidence interval estimation. Next is the hypothesis testing for the mean. If you want to test the hypothesis for mean, it will be a parametric test. We can either use z-test or we can use t-test for that. So here we say hypothesis test is a producer where claims about the value of a population parameter such as mu, that's the population mean, or population proportion, may be considered using the evidence from the sample. Also, we have what we call type 2 error. Type 1 error is good. You reject true H or true claim, true HO. Yeah, that's good. If something medicine is good and I reject it, is better than if your medicine is bad and I didn't reject it. So type 2 error is very dangerous, especially in the medical field like drug testing. Do not reject HO, but find defendant not guilty. Correct decision is here, and the bad decision is here. So correct decision, reject HO, find defendant guilty. Wait for a few seconds if it's okay. So as we mentioned earlier, there are 3 types of, when we are stating our HO and HA, we can either do a left-A test, right-A test, or two-way. Two-way test means equal or not equal. Left-A means HO will be greater or equal, then HA will be less. So right tail, the claim HO, the mu is less than or equal to mu O. Or HA then will be greater than. We can also, as we said earlier, use the p-value. But if it's two-way test, always when we get our p-value, we multiply by 2. P-value means whatever we set for the level of significance. If the p-value is less than the level of significance, then we are going to reject HO. Then we say the test is statistically significant. If the p is too big, bigger than the level of significance alpha, then again, we're going to fail to reject HO. Okay, so here they give the recommendations. If p-value is less than or equal to, this is very small, then we say this is extremely strong evidence, strength of evidence against HO. So if we have a strong evidence against HO, that means we are going to reject HO. Now here HO is very big, almost 15%. No evidence. So we cannot reject the claim. We fail to reject. Okay. Also here we can use this confidence interval. We can say the boundary, upper bound section, lower bound section. And the do not reject will be between lower bound, upper bound. Wait for a few seconds if it's okay. So this is a conclusion for 3 hypothesis tests using confidence interval. So we can see reject, do not reject, and here also reject. And the values given here, 0.5, 1.0, 2.4. So next, we also have the Z hypothesis testing may also be performed by the population proportion. And the test statistics is given towards Z data. Will be the P. So the first P is for the sample proportion minus population proportion divided by normally sample proportion will be the number of success divided by the sample size. As we said earlier, we can have the left tail, right tail, or two tail. Two tail means equal. Left tail means the HO cream, same as the mean. In this case, proportion will be greater than or equal to bar O. So for a few seconds, if it's okay. Okay. Okay, so that will be the conclusion. As we said earlier again, this is just to summarize, or I would say review the concept here. Now, let's look at our book, the classroom. One thing I mentioned is that I don't want to do the descriptive statistics, to be honest, but I put the lectures here. If you want to do the review on your own, that would be great. It's 149 slides, and I don't want to. I think we don't have to. This is the topic. Hopefully, we all know the frequency distribution, their graphs. For example, frequency table where you can, the goal of even doing frequency distribution is to organize your data. Your data should stay organized. And graphs will be to visualize your data. So we can start with a simple graph like histogram. If I have a frequency distribution or frequency table, we can convert it to histogram. Then the book talk about pie chart, column, bar, etc. So I don't know. Let's wait few. If we have to do it, I don't mind, but it will take the whole time. We can't do anything no more. Also, measure of central tendency, I think we don't need to. Finding the mean, median, mode. Measures of variation, how the data expand the spread. So in this case, we can use range, the difference between the maximum and the minimum value. We can find the variance. Variance value become too big because if we find the mean, we subtract each value from the mean and we add it together. Most of the time we are going to get 0, which we call the total deviation. 0 means the data are very close to each other. So deviation is not good. So we say, okay, next step, according to researchers, let's use variance rather. So variance means we find the difference of each value and the mean. Surely when you have a mean, some of the values will be less than mean, some of the values will be greater than mean. That's why you get positive and negative value, and later when you add all together, you get 0. Now, if a value is negative, if you square it, it becomes positive. If it's positive, you square it, it becomes positive. So that will lead us to, again, using variance. So after we find the difference of each value, we square, we add all the values, then we divide it by the sample size. I think normally we use sample size minus 1. If it's population, you divide by the population size. So in this case, you get variance, and the value will be big. So we normalize it by finding the square root of variance, and that gives us what we call the standard deviation. Then the measure of position will be Q1, Q2, Q3, quarter 1, 2, 3. 25%, quarter two is 50%, which is almost same as the median. So I think we shouldn't do this. So even if we say we're going to do it, we can't finish today. So that's all. That's the only review I'll give here. So let's look here. If we have any question, then we can review the part you have a question. But if I say I will take my time, go through how to find frequency, I mean, it's very, it will be time consuming. Why we have this, again, as we said earlier, let's go to the syllabus once. The syllabus is very, to make sure we are all in the same page. Where's the syllabus? You are lost. Oh, it's already the top. As we said earlier, again, there's no way we can be able to do all this work. This is this. Almost we finished the inference. Maybe we'll cover probability now. We already did regression. Let's forget about correlation, visualization. Maybe we'll do a little bit. But descriptive statistics, that's what we're saying. We need to skip that one. We don't need it. I'll wait. So again, I put the slides in the classroom. If you have any question, yeah, you can ask question about it. We don't have time to do it. So let's move forward. I'll wait for a few seconds if you have a question. So looking at the classroom, we did a univariate. We did a simple regression. So let's go to correlation, and that will be the end of it. So those are the ones that are selected. And the descriptive statistics, you have to do it on your own. So let's do the correlation. I think I opened the slide somewhere here. Yeah. So after correlation, we take a break. And hopefully we have enough time. Then we do a little bit of NumPy. The next week we do NumPy with pandas. Maybe we do some lab work in the class. Yeah. Actually, I have the Anaconda open. And I was trying to, yeah, I guess oh yeah, this is it. I was doing some examples here. So let's see if we can do it. Oh, I think I'll close it. Close it. Oh, no, right here. No. Oh, forget. I'll close it. Okay. I was running some. Okay, so let's go straight to correlation, then we take a quick break. So the correlation also will go very, not quick, but as we set it in a I'll say high level abstraction or abstract level. Yeah, so we will not go detail much. But I think correlation is a very small topic. I mean, small materials, because all we need to do is to find the R value. And we say the R value always is between -1 to +1, etc. But here we're going to discuss about two types of correlation. One is good for ordinal data and one is good for our regular data. So, I mean, quantitative data. So that's called a PSA. The PSA correlation, we use quantitative numerical values because to find it, sometimes we even have to find the mean standard deviation to plug into the formula. To find standard the Spearman correlation, we find something we call the D. It will be in some order. Again, we will discuss that. So Spearman is using ordinal data. Actually, in statistics, the only data or the only hypothesis test in non-parametric testing where we use the nominal data is the chi-square. Most of all the non-parametric testing, the data is in ordinal form. Likewise, same as Spearman. Yeah. So here we say two factors are correlated when what? The value of X has some predictive power on the value of Y. So if we have two variables, let's say S and Y, We can say they are correlated if one can have effect on the other one. But when we are doing regression, we have to identify which variable determine the other. So we have to know the independent variable and the dependent. When we are doing correlation analysis, we don't care. We don't, there's nothing like independent or dependent. We just want to know if the correlation value will be close to 1 or close to -1 or 0. Then we make our decision right there. So only in regression now we have to know which value will determine which value. Yeah. So here, for example, we say the correlation, as we said earlier, the value is range from -1 to +1. If it's close to 0 or 0, then there's no correlation. So here we say uncorrelated. First, we start with the PSC. As we said, PSC and SPMA correlation. PSC is parametric testing. SPMA is, again, non-parametric. The data is based on ordinal. So we say PSC correlation evaluate the linear relationship between two continuous variables. You have to be a value. SPMA correlation evaluate monotonic relationship. So this means SPMA correlation coefficient is based on what? Rank values for each variable instead of the raw data. And we'll see example here. I think we have example here. If not, there's another lecture slides that we can see the steps. So this is the PSC formula. And we see that again. It have to be var because we have to find a mean. There's another formula we can use which will tell us to find the z value. And forget the form. Yeah, z and s value. And we can use that also. Yeah. So here the n is the sample size. X and Y is our two data that we want to see if there's a relationship between them or an association. So this example, how we can represent PSC correlation value. SAT score and freshman, the GPA is 0.47. Not too good, but there's a positive correlation there, but not too good. So freshman, SAT score with a freshman. Next, we have SAT score and economic status. Income and coronary disease. Yeah, you see, this is very good. It's a very rare data. You see, it's -0.717. Because if a person receives a very high income, like the president of in the company or even the country, they have the best medical system in the world, in that country. Yeah. So if a person have a very high income, most likely it's in a high position in the company or the country or government job. So they get the best medical billing, the best salary, the best everything. So the R value is very good, which means if your income is high, you're not going to have too much disease. Here we are talking about coronary disease. If your income is low, even just to go to annual checkups, if it's a problem, then we have the coronary disease. Let's see the other one too. I think it's a rare data. Smoking and mortality rate, let's say consider with lung cancer or something. Yeah, the more you smoke, the more chance of lung cancer than mortality. Yeah, so it's 0.717 decreasing. Video game and violent behavior. Earlier time when the video game were starting, people say, your children shouldn't play video game, especially the violent games that lead children to be committing. But later, there's a lot of research done, and they found out there's no any correlation between video game and violent behavior. Here, I'm talking about violent video games. It doesn't lead a person to be a violent person. So the R value is good. I think all these data sets, all these are, maybe it's a rare research that they did to give to us. So next, we interpret what is actual. I'll skip this. We just discussed that already in the regression when we go through that R square. So the same thing they said, the square of the sample correlation, which is the R square always estimate the fraction of the variance in y that was explained by x in a simple linear regression. So I think we did simple linear regression already. So actually we did it today. So I'm going to skip that section. Yeah, so let's come to Spearman rank correlation. So we say Spearman rank correlation, we can count the number of disorder pairs, but not how well the data fits a line. So that's better with nonlinear relationship and outlines. So we can see the three data. First one, the Spearman is almost, PSA give 0.69. Second one, both of them are around the same. Third one, PSC didn't do good. Now, it depends, as we said, the order of the data, but let's see, I think there's yeah, so this is it. So to do the Spearman correlation, as we said, the data must be in order. So we rank, first of all, we have to, if we have S and Y, we are going to rank them. Then we find the differences that will give us the D. Then sum them, then we use so we can see we sum all the D square times 6 over N will be the sample size again. So that's then the result we get is subtract from 1. That will give us again the Spearman correlation. So it's based on ranking. You see here the DI is what? Rank XI minus rank Y. So the difference of X and Y, the two variables here, finding the correlation. The data also, the value also have to be the same as PSC. It ranges from -1 to +1. So now we know about this correlation versus causation. Example that I saw a few years back, always I use it as example in the stat textbook, is, for example, we are in Florida. I think it was Florida. In Florida, during the summertime, shark attack increases a lot. Shark attack in the ocean increases. The reason why, because the water get warmer and the shark, they come close to where people swimming. At the same time, in the summer, ice cream sales go high, especially in the Florida is almost all year summer, but in the actual summer, it's more hot than December, etc. Yeah. So ice cream sales goes up. So if you collect the data, it's very difficult for us to say that, okay, if person get attacked by shark, he's going to buy ice cream. Or if a person buy ice cream and he go to the ocean, he's going to be attacked by a shark. Yeah, I think that's impossible. So that's what we mean by correlation does not mean causation. Actually, sometimes we may have another variable we call the confounding variable, or sometimes they use the term locking. That's Lurking, locking variable. This will be a third variable that can bring that relationship up. So in the case of Florida, our third variable will be the temperature. So it's the warmer the temperature caused that correlation between ice cream sales and shark attack. And a nice example they gave you also. For example, the number of police active in a precinct correlated strongly with the local crime rate. But, of course, the policeman didn't cause the crime. Yeah. So, yeah, there's a correlation there. In Bronx, we have a lot of police officers. But it's not the police officers cause the crime. It's just the crime rate is the associate. Yeah. And that will be the conclusion of this. Again, as we said, we just want to summarize everything quick so we can cover as much as we can. We're almost 2 hours now. So I think time to take a break. We did very perfect. So what will happen is that when we come back, we are going to cover the I don't think we should cover anything here no more. We just go straight to NumPy. Statistical modeling, probability. Yeah, maybe we can cover probability distribution a little bit. Again, this will be high. We are not going to go detail how the binomial distribution work, the formula to do it, the try. Maybe we're just going to talk about what is a binomial distribution. And also what kind of condition we may say something is binomially or something. Maybe the number of try outcomes should be only true or false. That's why it's binomial timing. Like Poisson will go with the time interval. I said, so maybe we just discuss something like that, but we shall not go detail again. So let's do that. Then we make sure we finish the whole week 6. Next week, when we come back next week, we do NumPy. And it will be very slow because we're going to do some practical work, lab work on this. Yeah. Pandas also we may see a little bit. So today is the last day. From next week, week 6, 7, and 8 before midterm exam, a lot of hands-on work throughout the midterm exam. Okay, so if no question, I think let's take a break now. And I think I was not recording, I'm not sure. Oh, I was recording. Okay, that's good.